We present 3D human pose perception from egocentric stereo videos. Recently, 3D human motion capture from first-person views received increased attention. Portable devices recording egocentric views are becoming more and more compact, with the most recent ones being the eyeglasses-based stereo setups of EgoGlass and UnrealEgo. However, existing stereo-based methods do not deliver the 3D reconstruction accuracy desired in many applications. One of the reasons is that they do not utilize temporal or scene information contained in the input egocentric views. Furthermore, only a single synthetic data accounting for the eyeglasses-based setting is currently publicly available. Hence, extended eyeglasses-based stereo datasets would be required for an extensive evaluation of existing and upcoming methods. The central contribution of this paper is a new framework for 3D pose estimation from egocentric stereo videos. Our neural approach effectively utilizes scene information and temporal context of the input stereo videos. We also introduce two new benchmark datasets recorded in synthetic and real-world environments. The proposed framework is designed to leverage scene information and the temporal context of egocentric stereo videos. Firstly, the framework takes an egocentric stereo video as input. From those, the 2D module estimates 2D joint heat maps. The estimated heat maps and the input videos are then processed in the segmentation module to obtain 2D human body masks. Next, we use uniformly sampled windows of input frames and human body masks to reconstruct a 3D scene via structure from motion. Here, we render depth maps and depth region masks from the reconstructed mesh. Note that in our challenging eyeglasses-based setup, the 3D scene and camera poses cannot always be estimated due to severe self-occlusions in the egocentric images. This results in corrupted depth maps and, consequently, unreliable network gradients during training. The current diagram shows an example of invalid depth values for the second input frame, which is tackled later in our 3D module. The 3D module adopts a transformer decoder to estimate accurate 3D poses from the depth data, heat map features, and human joint queries. It first extracts features from depth maps and heat maps using convolutional layers. Next, we add depth padding masks to the depth features before the softmax activation function of the self-attention transformer layers. With the padding masks, the network avoids processing the depth data with invalid values when estimating 3D poses with joint queries. Furthermore, we enhance the joint queries with our video-dependent joint query adaptation technique. Specifically, we extract stereo features at each time step from the 2D module and combine them to obtain a stereo video feature. This feature is used to augment joint queries to boost 3D pose estimation accuracy. The first proposed benchmark dataset is UnrealEgo2. To create it, we adapt the publicly available setup and assets with a virtual eyeglasses device for stereo view capture in a synthetic environment. Here, we show example scenes from UnrealEgo2. UnrealEgo2 offers simple to highly complex motions, such as walking, crouching, and crawling, to name a few. In total, we render 2.5 million egocentric stereo views with the corresponding ground truth 3D poses. The second benchmark dataset is UnrealEgo-RW, a new real-world dataset with various human motions recorded in a multi-view 3D human motion capture studio. The captured subjects are wearing the newly developed portable device emulating the eyeglasses-based setup. Here, we show example scenes from UnrealEgo-RW. UnrealEgo-RW contains motions ranging from simple to highly challenging ones, such as kicking, crawling, and dancing, to name a few. In total, we captured 260,000 egocentric views with ground truth 3D poses. These tables summarize the quantitative results on UnrealEgo and our proposed datasets. Our approach outperforms existing methods by a significant margin across all metrics. We next visualize qualitative results. Compared to the existing methods, our approach handles fast and complex motions more accurately on UnrealEgo2. On UnrealEgo-RW, our approach likewise yields better 3D reconstructions than the previous methods. Our method can also be applied to stereo videos recorded in the wild. It robustly and steadily estimates accurate 3D poses. Thank you for watching our video. UnrealEgo2, UnrealEgo-RW, and our trained models are available on our project and benchmark challenge pages.